So let's get started. What I want to do today is I want to recap part of the discussion we had on Thursday on work and energy and electrostatics. I want to continue that. I want to finalize the mathematical framework that we were developing to calculate the energy of the formation of a point charge distribution. Okay, we do one simple example to establish what the formulation really means, and then we're going to move on to energy of a continuous charge distribution. Basically, we start with the point charges, and as we did that number of times already in this course, we're going to assume that every continuous charge distribution is basically a combination of many point charges. I'm going to do a couple of examples on this, and then I'm going to discuss a few points on electrostatics energy. If we have more time, it doesn't usually happen. If we have more time, I'm going to talk about conductors as well, but let's see. Okay, so the idea was it takes energy to create a certain distribution and collection of point charges. Okay, and what we discussed was basically on the foundation that imagine you have a charge, let's say I'm going to call that Q, a test charge, you're moving it in a space where we have electric field as well. Okay, imagine this is electric field. And then if you want to move this charge, okay, if you want to move this charge from point A all the way to point B, what you need to do is that you need to overcome the electrostatic forces, okay? So it could be repulsion or it could be attraction, but whatever that force is, if you want to make that move, you need to overcome the force of the electrostatics, okay? So the force of the electrostatic, of the electric field is Q times E, and if you want to overcome this, you need to exert a force of negative QE along this path. Okay, so if you want to calculate, how much work it takes, you need to integrate F dot dl from point A to point B. Okay, and this F is negative Q. Q is being a constant over the course of this displacement. So it's going to be negative Q out of integral E dot dl, okay? And if you look at this integral, which runs from A to B, this is the definition of the VB electric potential at B minus electric potential at A, okay? Of course, this includes this negative sign as well. So the work that we need to do to make that movement possible is equal to electric charge times the electric potential difference between the final position and initial position of the path. Okay. So, and if we are bringing this particle from all the way from infinity to A, this will be equal to negative of Q times VB. Okay. Okay, let me double check the sign here. Sounds good. VB minus 3I. Okay, so if VA is at infinity, VA is 0, and then we will have Q times VB, and we don't have negative sign here. Okay, so if you're bringing one particle all the way from infinity to a certain point that we already know what electric potential is, we don't really need to care about the path, we don't really need to care about anything else. As long as we know potential at that point, the work it takes is Q times VB. Okay, so with this foundation, we next started looking at a collection of point charges, and the way we had the discussion was we assumed that we bring the first particle, and then we bring the next particle, and we bring the third particle, and so on. And we tried to formulate all the work that takes to bring all these charges one after another. Okay, so let's repeat that one. And then we're gonna follow these to calculate any work. Okay, so let's imagine we bring 1 point charge. I'm gonna call that Q1 from all the way infinity to this point. But this is the very first point charge, okay? And we assume that everything else is just vacuum. There's nothing else in this space, okay? So bringing this one to this point does not take any energy because there's nothing to interact with this Q1, okay? But if you bring another one, Q2, okay, then it takes some energy to do this, okay? And the energy of that, I'm gonna call that W2. Following this one, we are bringing the charge Q2, and then we calculate the potential created by charge number 1. I'm gonna call that U1 at the position of R2, where we are placing the second point charge, okay? And this is going to be equal to 1 over 4 pi epsilon 0 Q1 Q2 divided by R12. And R12 is the distance vector between number 1 and number 2. Okay. And then if you bring another particle, let's say number 3, Q3, to this point, what we have is Q3 interacting with both of number 1 and number 2, and the work needed to bring this W3 is Q3 times V1 at R3 plus Q3 times V2 at R3. Okay, and that's going to be equal to 1 over 4 pi epsilon 0 Q1 Q3 R13 plus Q2 Q3 R23. Okay. So this is how much energy it takes to bring number 3, okay? So if you want to have only this collection of three particles, 3 point charges, by the way, this is R13 and this is R23, okay? If you want to have this collection, the total energy is W2 plus W3. If you write it, it's gonna have the form of V total. It's going to be 1 over 4 pi epsilon 0 Q1 Q2 divided by R12 plus Q1 Q3 divided by 1R3 plus Q2 Q3 divided by R23. Okay. If we want to bring number 4, the number 4 is going to interact with all of these as well, okay? So if we have n particles, n point charges, the total W, the total work can be written in terms of 2 summation, 1 over 4 pi epsilon 0 summation over I that runs from 1 to n times summation over j with the values of bigger than I all the way to n. And then we have qi, qj divided by rij. Okay, so we're gonna have a summation like this. And we said the reason we use j greater than I is that we want to avoid double counting. Okay, so if we have a term like Q2, Q3, we don't want to have exactly similar term Q3 times Q1 divided by R32. Those terms are equal, exactly the same as each other, but we want to avoid that in the summation. Okay, so one way to avoid that is starting counting j with the values that are greater than I. Okay, so this way we only take pairwise interactions. We count pairwise interaction only once. Okay. The problem with this is that this is a difficult notation to deal with. Another way is intentionally counting everything twice, but then at the end divided by 2. Okay. So what you can do is that we can make it 1/2, let's do it easier, times 1 over 4 pi epsilon 0. And then we have a sigma over I, 1 to n, another sigma over j, 1 to n, times qi, qj, rij. Okay, so here the difference is that j starts from 1, and we know that with this summation, we are double counting any pairwise interaction, we are counting twice, but then I use a factor of 1/2 to divide it by 2. This is much nicer way to deal with this summation. Okay, so far so good? Everyone is following here?
Yeah.
Okay, we got 16 students. Okay, so this one, we can rearrange things and come up with a much nicer explanation of the total work, which is technically the total energy required to create this collection of charge distributions. Okay, so I'm going to erase some of this stuff up here. I'm going to continue here. So let's consider this as well. Okay. So I'm going to take this, and then I'm going to note that here, the second summation is on the j. Okay, so rij is dependent on j. Qj is dependent on j as well, but qi is not dependent on j. Okay, so these can be taken out of this summation and can be moved all the way here. Okay. And 1 over 4 pi epsilon 0 is a constant. It's nice to keep it outside of the summations, but if I move it inside, that's going to have a nice meaning. Okay, so let's do that. I'm going to start saying that this W is, so we had that factor, the 1/2 coefficient here. So I'm going to change it to now sigma over I from 1 to n. Okay, so all I'm doing here is that I'm just rearranging the parameters here, okay, nothing else. I'm going to start from this summation, I from 1 to n, okay, and I'm going to say this is qi, so this is the qi that I was taking out of this summation, times 1 over 4 pi epsilon 0, summation over qj, divided by rij. Okay, and I'm going to put this in the parentheses. Okay, so what is this one, the term in the parentheses? It's 1 over 4 pi epsilon 0 qj divided by rij. And this is basically the potential, the electric potential at position Ri where this charge sits, and this is the potential created by all all point charges except the Qi. Okay, so the whole summation is VRI, and that refers to electric potential created by all charges except I, right at the position of Qi. Okay, so in a much nicer way, we can write it in terms of 1 sigma I from 1 to n Qi VRI. Okay, so this is electric charge, this is potential, and this summation runs over all the charges. Okay, so if you have a collection of point charges, no matter how many charges you have, you just need to calculate first potential at the position of every single charge created by other charges and multiply by the charge of that, that charge and sum over all of them. Okay, so I'm going to do one simple example to see so that you can see how you can use this and calculate the point charge distribution's energy. Okay, so far so good. Is it clear how I moved from here to here and how from here to here? Yes? Thumbs up? Thumb? Good.
Yes.
Okay. So I'm going to keep this and I'm going to do one simple example, which is, I think is a problem from textbook. So let's consider this. So the example is basically problem 2.31 from the textbook. And we have a simple collection of 4 point charges sitting on the edge of a square with distance a, and the point charges have the charges of minus q, plus q, minus q, plus q. Okay, and the question is how much energy it takes to bring all these charges together and keep them in such setting. Okay, so how many charges we have? We have 4 charges. So I runs from 1 to 4. Okay, and then what we need to do is we need to calculate the potential at each of these corners. Okay, so what is the potential at the top left corner created by the rest of the charges? Pretty simple, I would say. Just following what electric potential is created by point charge. We have 2 charges, positive Q, 1 charge, negative Q. So if I want to name this 1, 2, 3, and 4, I would say V, electric potential at R1, created by 3 other charges, not the charge number 1 itself, is going to be 1 over 4 pi epsilon 0. We have 2 positive Q's, so 2Q divided by the distance of each of them to this is A, plus negative Q divided by the distance here is diagonal, so it's going to be a square root of. Okay, and if we pull out the Q over A factors, we get 1 over 4 pi epsilon 0 q over a times 2 minus 1 over the square root of 2 is basically a square root of 2 by 2. Okay, so this is V at R1. Okay, so because of the symmetry, we can say V at R3 is going to be the same. So this is exactly equal to V at R3. And then V at R2 and R4 have exactly the same shape, but the charges are negative and the other one positive. So it's going to be negative of what we have here. So V at R2 is going to be equal to V at R4. And that's going to be exactly like this, but negative sign. So it's going to be 1 over 4 pi epsilon 0 q over a square root of 2 by 2 minus 2. Sounds good? So here we are calculating potentials, and then energy is simply charge multiplied by this potential divided by 2. Again, so whatever contribution we have from 1 should be exactly the same as 3. Okay, so we get 2 contribution from these 2, and combined it's going to be, so I'm going to say from 1 and 3, we're going to have energy being 1 over 4 pi epsilon 0 q divided by a times 2 minus the square root of 2. Okay, so technically there was a factor of 1/2, but now we are 2 of the charges, so I'm canceling that out. So this is contribution from 1 and 2, and then from 2 and 3. Okay, sorry, I missed something here. These charges have, this is the potential, and the charges have the electric charge of negative q, so I will have a negative sign here and q squared here. From 2 and 4, exactly same potential, exactly same charges. Okay, so I get 1 over 4 pi epsilon 0. Here these two are inverse, so I'm going to put a negative sign to include that, and then q2 over a, 2 minus the square root of 2 divided by 2. Okay, so if you look at these contributions, look very similar to each other. Okay, and if we add them up, W total is going to be negative 1 over 4 pi epsilon 0 q2 over a times 2, technically we get 4 minus the square root of 2. Sounds good? Clear more or less? So we first calculated the potential, electric potential at any position.
Avoid delete.
Question?
File open. Colors text.
Okay, I think you think you're mute, you're not, but that's fine. Okay, so any question from here?
Yeah,
Clear?
I do have a question. I have a question.
Sure.
So for BR1, can you, that's from...
Can you speak a little louder so that I hear this and everybody hears as well?
Can you go over from the process of BR1? Just so I can...
Okay, yes.
Yeah.
Okay, so 1 over 4 pi epsilon 0 q over a is the potential created by any of these charges, number 4 or number 2 at the position of the charge number 1. Okay, so I have 2 of these. That's why I have a factor of 2 here. That includes 4 and 2. And I have negative of the square root of 2 over 2, which is potential created by 3. So this comes from 2 and 4, and this term comes from 3. Okay, 3 is diagonal, so I need to use 1 over square root of 2, which is equal to square root of 2 by 2. Cool?
Yeah, I get it now. I get it now.
And the same goes for VR2 and VR4. The only difference is that at 2 and 4, the charges and the distances and arrangement is almost negative of what we have for R1 and R3. Okay, so I just switched this one. But at the end, when we're calculating the energies, because the charges are opposite to each other as well, the contribution from 1 and 3 and 2 and 3, they are exactly the same, with the same sign and everything. Cool? Good. So this was just an example to show you how you can add up those, how you can calculate the energy, how you can calculate the electric potential and energies by multiplying Q by V and then summing over all charges, and of course divided by 2. Okay, so if there's no question on this, I'm going to move on to energy of a continuous charge distribution. Okay, so let me get rid of all this. Okay. So, in one hand, let's consider we have these point charges, and we said the energy to create such formation is 1/2 sigma I1 to N QI times V RI. Okay. So we have these 4 point charges. And now let's consider we have a continuous charge distribution, okay, and with volume charge density of rho, okay. So converting this to an integral for continuous charge, we get 1/2, of course, and then integral of V dq, which in case of volume charge density, that becomes 1/2 times V rho theta. Okay. And this integral, of course, runs over the volume that we have, volume charge density, but it's okay to increase it all the way to infinity, and we're going to discuss that next in a bit. Because if you extend the limit of integral, you are including the areas that there's no volume charge density, means rho being 0. So it's okay to just increase the limit of integral and expand it all the way to infinity. Okay. So this is for continuous charge distribution. Okay. And there's a very nice way to change this integral and write it in terms of the electric field. As you can say, electric potential is related to the electric field, okay, by the relationship of E being negative of gradient of V. And charge distribution is also related to electric field through the differential form of the Gauss law, where rho over epsilon 0 is equal to the divergence of E. Okay. So this integral, what I'm going to do next is that I'm going to expand this integral, writing that in terms of the electric field and potential, and then through a trick, I'm going to finalize and come up with an expression, mathematical expression, that the energy for the electrostatic system can be calculated based on an integral, only integral of an electric field. Okay, and that's going to be very useful, and that's something that we're going to use it in later chapters, even when we are talking about the electromagnetic radiation. Okay, so we're going to come up with an expression that tells us what is the density of energy in an electric field. Okay, so to do this, I'm going to start from here and write the charge density in terms of the electric field. So W is 1/2 V times rho theta. Okay, where rho can be written in terms of epsilon 0, divergence of E. Times theta. Okay, so this is an integral over volume, and this is over volume as well. And I change rho to divergence of E, and of course we need an epsilon factor, which is now outside integral. Okay, so this integral, we can do integration by parts. Okay, so you may refer to equation 1.59 from chapter 1, how you can do integration by parts when you have divergence, and that becomes two integrals. Okay, we have epsilon 0 by 2 here, and then we have two integrals. The first one is negative of E dot gradient of V theta, and this integral runs over volume. The second integral is an integral over closed surface of V, the electric potential, times E electric field times dA. Okay, so the first integral over volume, the same volume that we have charge distribution, and the second integral is on a surface, which is surface encapsulating this volume. Okay, now if you look at this, we have negative sign here, and this is the gradient of V, which is simply negative electric field. Okay, and the second one, we can't really simplify it more, but there's a way to get rid of the second one. So I'm going to rewrite this. The first one becomes nicely, the negative cancels, they cancel out each other. So we get integral of E2. Here we have E dot E becomes magnitude of E to the power of 2 times d theta over the volume, plus the second one, which is epsilon 0 by 2 times integral over the surface of V ADA. Okay, so there's something very nice and specific about these two terms. Okay, so if we have a charge distribution like this, and if we integrate electric field over V, which could be only the volume that we have, the charge distribution, plus this integral is going to give us the energy. Okay, so now I want to argue something. What if instead of only covering the volume that has volume charge density, if I make the limit of the integrals a little bigger and include a volume, something like this, what happens? Let's discuss it from two perspectives. One perspective is the first integral that we started from. 1/2 V times rho times d theta. Okay. If we are within the volume that we have charge distribution, rho has some values, which is non-zero. If we include anything here, rho is 0. Okay. So technically moving the limit of integrals from the small volume to a bigger volume does not change W at all. Okay, because you are including certain parts that has no volume charge density whatsoever. Okay, so we are free to increase the volume on which we are doing the integral, carrying out the integral without changing the outcome. Okay, so we are free on this. And this W is exactly the same W. Okay, but now look at the two terms in this integral. Okay, The first one is electric field to the power of 2 divided by d tau. Okay, so I want to ask you this. Do you expect us to have any electric field outside where we have charge distribution? Yes or no?
Let's say no.
Okay, why not? You have all this charge distribution here. Don't they create an electric field outside? Of course they do, right? If you have charge distribution here, it creates electric field from outside here all the way to infinity, okay? So here, if we increase the limit of the integral, the value of the first term does increase, okay? But the value of the combination of the first term plus the second term does not change because the W, the work here, does not change and it's not dependent on the limit of the integral. What happens is that if you make this volume bigger, the contribution from the first term, which is integral over volume, increases, and the contribution from the second term, which is integral over the surface, decreases. Okay. And what happens here is that as you move further and further away from our charge distribution, both electric potential and electric field decrease in value. And since this integral is only on the surface, if we move all the way to infinity, the electric potential and electric field value drop so much so that if you do this integral over this surface, the whole integral becomes zero. Okay, so we are free to change the limit of integral and make it bigger and bigger. And what we are doing by that, we are not changing the value of the work we are calculating. We are just changing the balance between the first term and the second term. The first term increases, the second term decreases to the point that the contribution of the second term becomes an absolute zero. And all the energy can be calculated based on the first term if we extend the limit all the way to infinity. Okay, so I want to say that the whole work is equal to integral of the first term, okay, with changing the limit from V to a limit that includes all space. Okay, does it make sense? It's a good time to ask question.
So it's no longer, I have a question. So it's no longer the shape that we're integrating, it's actually all space, like you said, because it's making an electric field. And if I understood this correctly, the other closed integral doesn't really count for much since it's limited to the surface.
Yes, if we make the surface bigger and bigger, the contribution from the second term, which is the surface integral, that becomes smaller and smaller. And the contribution from the first integral becomes bigger and bigger in a way that the combination does not change. Okay, so if you want to define the limit of the integral, the minimum limit is including every part of this space that we have charge distribution, the minimum. But we can always, we are free to increase that limit and include part of the space that does not include charge distribution. Okay, so that's the basic thing about the V. If you are writing in terms of these two, the bigger the volume we choose, the more important the first term, the less important the second term. Okay, and if you include all the space all the way to infinity, what happens is that the contribution of this term just vanish, and we can only look at the first term to calculate the total energy of the electric charge distribution.
So if we move the volume out all the way to infinity, so we're taking the integral of all space, it becomes the integral of the surface area with respect to the area,
The surface area just becomes zero if you extend it to infinity. Okay.
Okay, because I'm looking at the third.
Yes.
I'm looking at the third equation, the third integral, and it says E squared dA.
Oh, sorry, that's the type.
Yeah, I was a little confused about that. Yeah.
Yeah.
Yeah, okay, so it is d tau then. Okay.
This is just the first term with the limit
Okay.
to all space.
Okay. Yeah. I was a little confused. Like, wait, why are we taking? Yeah. Okay. Thank you.
Yes. Okay, I get it. Thanks for pointing that out.
So the integral that says all space is the main integral, because since it's generating an electric field and it's increasing with volume, the other closed integral doesn't. It eventually approaches to zero as you increase the volume.
Yes, yes, exactly. Sounds good?
Yep.
How about I do one example on this on a relatively simple case, and then you see how this calculates the energy and also how this calculates the energy, and you will see at the end these are the same. How about that?
Sounds good.
I think it helps. Okay. So let's stop this discussion here. I'm going to write these two terms on the side, and then we're going to do one example. Okay. So let's write both equations. One of them was integrating VdQ over volume where we have charge distribution, and the other one is integrating epsilon 0 by 2 integral of E2 d tau over all space. Okay. So, and all I did in the last, not last slide, but last discussion here, these two are the same. Okay, and sometimes it's easier to use these, sometimes it's easier to use these, and eventually we're gonna have a lot more focus on these when we are talking about the electromagnetic waves and radiation. Okay, so one relatively simple example, which is from the textbook, this is example 2.9.
Professor,
Yes.
for the second equation, isn't it supposed to be dA? Or is it d tau?
This one, this is d tau. This is over the volume of all space.
Okay.
Okay, so that was a typo. I wrote dA in bottom here, and I corrected that. Someone pointed
Oh,
out.
okay. I didn't catch it. All right. Thank you.
Okay. So imagine
Open.
you have a spherical shell, okay, with a charge density of sigma, okay, and we have the total charge of Q, which is equal to 4 pi r square sigma, distributed on the surface of this sphere, okay, and basically on this shell. Okay, the question is, what is the energy of this uniformly charged sphere, uniformly charged shell? Okay, so there are two ways to go about it. One way is calculating the electric potential. So I'm going to say solution one. One way is to calculate electric potential at position R, which is, I'm going to write, this is electric potential on the surface of the shell, okay, and do the first integral, okay, and following that, W is half integral of V on the surface. dQ is basically sigma times dA. The charge distribution is uniform on the surface of the shell. The electric potential is uniform on the surface of the shell. So the combination is going to be simply, let's continue here. It's going to be 1/2 times V R times sigma times 4 pi r square. And VR is the potential on the surface of the shell. We did it previously as an example, and that is 1 over 4 pi epsilon 0 Q over R. And the combination is going to be, so here we have 4 pi R squared times sigma. That itself as a combination is a total charge on the surface. Okay, so it's going to be 1 over 8 pi epsilon 0 Q2 over R. Okay, so let me check with, yeah. Okay, so this is the energy of such charge distribution based on doing the first integral, which is 1/2 V dq. Okay, so here what we did, we looked at the electric potential right at the point that we have charge distribution, and then we added up all the contribution of potential times charge. Okay, so we were so focused only on the surface of the shell where we have charge distribution without caring what happens outside. Okay, so this is one way we can calculate the energy. The other way, based on the second approach, I'm going to call this equation number 2, is only focusing on electric field. Okay, and if you want to only focus on electric field is created and expands everywhere all the way to infinity. Okay, so if you want to do that, you want to look at the electric field in the whole space from 0 to infinity. Okay. So if I want to follow approach number 2, no, let me box this away. This is solution number 1. And then I'm going to do solution number 2 here. I'm going to follow this. So what I need to do is that I need to calculate electric field everywhere in a space. And we did that as well in previous examples. Inside the shell, we had found that electric field is 0. There's no electric field. Outside the shell, electric field was very similar to the electric field created by a point charge, and that was 1 over 4 pi epsilon 0 Q divided by R squared times R hat. Okay, and if this is E, then the electric field to the power of 2, which is technically the integrand here, is 1 over 16 pi square epsilon 0 square Q2 R4. Okay, and we need to integrate this from all the way from the surface of the sphere all the way to infinity. Okay, so the integral we need to do following the second approach is epsilon 0 divided by 2 times E square is what we have here. And we have a bunch of constants, so let's write them separately outside the integral. And that is Q2 over 16 pi square epsilon 0 to power of 2 times here. The only R dependent term is 1 over R square. Sorry, 1 over R to the power of 2 times d tau. D tau is volume element in a spherical coordinate. And if you remember, the tau in a spherical coordinate should be, I'm going to create a box here. The tau is R square sine theta dr d theta d phi. Okay, so this d tau becomes R square sine theta dr d theta d phi. Okay, now you see the first term R square cancels out with 2 of the R's in the denominator, so I'm going to write it 1 over r squared. The integral over d phi, the integrand is not dependent on phi, so d phi, which runs from 0 to 2 pi, gives me a factor of 2 pi. So I'm going to use that, write that here. And then we have the integral of sine theta d theta. Theta runs from 0 to pi, and that's going to give me a factor of 2. I'm going to add that up here as well. So this is the integral of sine theta d theta from 0 to pi. And this one here is the integral of d phi from 0 to 2 pi. Okay. So at the end, I have this integrand of dr over r squared, which runs from r being equal to capital R, the radius of the shell, all the way to infinity. Okay. So let's clean up here a little bit. We have a bunch of factors that can be canceled out. The epsilon can be canceled out with the exponent here. We have 2 and 2, then 4 pi. Technically, we have 16 pi. So these cancel out with the 16 pi squared, make it 4 pi. Okay. So combination, as a whole, we get q squared in the numerator. We get 2 times 4 pi epsilon, which is 8 pi epsilon in the denominator. And then we get this integral of dr over r squared from r to infinity. This integral is 1 over r with the limit of infinity and r. And in fact, this integral is negative of 1 over r. Okay, so at the limit of infinity, 1 over r is 0. At the limit of r, it becomes 1 over r, and the solution finally is 1 over 8 pi epsilon 0. The denominator here, q squared, which is numerator here, divided by r. Okay, so as you see, and as we expected, the energy calculated from second solution is exactly the same as the energy we calculated from the first solution. Okay, so that's what we expected. Mathematically, we have shown that these two are the same. Physically, they can have very different concept, okay? In the first integral, the first approach, what we did, we only focused on where we have the charge distribution. We look at the electric potential right at those points and calculate the total energy, okay? The second one refers to a concept that we claim that there is an energy associated with electric field. There's always an energy charge density associated with electric field. And in order to calculate energy, we look at the electric field wherever we have electric field in a space. And that actually runs from the surface of the shell all the way to infinity. Okay, so in the second approach, we integrated that one. Okay, we integrated E squared over the whole space, but what it should happen, and did happen, is that whatever approach you choose to calculate energy, at the end, you should come up with the same answer. Okay, so I hope this example cleared up what it means using this approach and what each of them really focuses on. Any question? No? Is it better now? More clear? Okay. Okay, things like this, I really want you to read the textbook and do this example on your own as well, okay? And also do the mathematics that I had on the previous page that we started from here, and we showed that mathematically these two are equivalent to each other. I want you to really do that once, have a pen and paper in your hand, and that way you will develop more of intuition for yourself. Sounds good?
Sounds good.
Okay. Okay, so I'm going to discuss a few comments about the electrostatic energy and everything we discussed here. And by that, I will be concluding the topic of work and energy. And next time, we're going to move on to discuss conductors, which is going to be next Tuesday. So I anticipate that I'm going to finish chapter 2 next week on Thursday, and then we will have quiz and assignments the week after. Okay, so 2 weeks from today. Okay, so let me erase these things, and I'm going to discuss 3 points about the energies. Okay, so the first point is I'm going to ask energy negative or positive. Okay, so something very interesting. If you look at this, here we integrate v dot dq. Okay, and this comes exactly from the point that we said the total energy is for point charge distribution is 1/2 sigma over qi v ri. Okay. Now I want to give you one example. Let's imagine you only have one negative charge, negative q, and you have one positive charge, positive q. Okay. Sitting a distance r from each other. Okay. If you follow this, what is the energy of this charge distribution? You have two charges, so it becomes 1/4πε0. Q1 times Q2 becomes negative Q squared divided by R. Okay, now, is it negative or positive? Are you guys with me? 1/4πε0 negative Q squared divided by R is actually a negative number, okay? So this is negative. Now look at this equation number 2, where you have W is epsilon 0 by 2 E squared times D tau. Okay, so is this negative or positive?
Positive.
Positive?
Can it ever be negative?
No.
No.
It cannot ever be negative because we have magnitude of e to the power of 2. This integral is always positive. Okay, so what's happening? We started from here. From here, we moved to continuous charge distribution, and then we moved here. So technically, these three are supposed to be exactly the same. From here to here, and from here to here. They are supposed to be exactly the same. How come we are getting something negative here, and we can't ever get anything negative if we follow this? Can you guess what happened? At some point during this transition, certain logic breaks down. Okay, not that any of them are incorrect, they are actually all correct, but they just refer to different energies with different logics. Okay, so can you guess what happened here?
Is it the fact that we're integrating over all space? So you just have a total number for the work?
Okay,
Basically like a magnitude instead of a...
The logic from here to here is correct, okay? So there's nothing wrong between these two, in a way. You know what? Maybe No, I think from here to here, this should be consistent. The difference is something else. Some limit of the integral is being changed when we move from here, the point charge, to continuous charge distribution. That's where the something is breaking down. Okay, so let me start by something else. What is a point charge? Point charge is technically like one sphere or one shell that you make it squeeze it to very, very, very tiny space, right? That's the point charge.
Oh, can I try?
Yes.
Is it because since we make it like whatever we're doing, we technically consider as a point charge, then there's nothing to compare it to, so there's just one charge instead of negative positive?
Okay, that's, I think, relatively correct. Here is the point. There is no actual point charge in space. Any point charge that we discuss is technically one sphere or something that is squeezing the super, super small. Okay. If we follow this one, we are already assuming there is no energy associated with the point charge itself. Okay, so if you follow this, that means that if you have one single charge in space, and that's what we started discussion in this lecture. And I said, if we have one point charge, there's no energy associated with that because you bring that charge from infinity to here. Okay, so that's what the assumption of a point charge is. If you look at the continuous charge distribution, point charge can be a continuous charge distribution so focused on a tiny space. And that's technically one sphere, okay? And if you follow this, on a point charge, even one single point charge has a lot of energy associated with itself, and that's always a positive energy, okay? Going back to the previous example, we said if we have a spherical shell, the energy associated with this is 1 over 8 pi epsilon 0 q square, which is a charge on this, divided by r, which is the radius of the shell. Okay, now imagine you squeeze this shell and make it a point charge. What are you doing? You are making r smaller, okay? Whether q is positive or negative, you are making r smaller to the point that you are increasing the contribution of this self-energy to some very, very big positive number. Okay, so if you do this for every single point charge that you might have in your system, right, you're gonna get definitely positive number. You are not gonna get ever a negative number, okay? What is happening in this equation is that it's calculating all the energies except the self-energy of the point charges, and that can be negative, okay? But then if you want to follow and include all the energies in the system, they will be positive, regardless of the charges and whether you have negative and positive sitting next to each other. The energy of the electric field, okay, whatever charge distribution you have is gonna be positive. If you put aside the self-energy, then you might give something negative like this, okay? So the difference between this being negative and this being positive is that this does not include the self-energy of the point charges.
For the equation in the that you squared off, is that
This one?
no, the on the bottom?
This one?
Yeah, what's in the denominator, the first term?
The denominator is 8 pi epsilon 0.
Oh, gotcha.
This is the same example I just did, right?
Oh, okay.
Okay, and just to show that if you squeeze all the charges and make r smaller and smaller, you make the self-energy going all the way to infinity. And that's going to be positive infinity. Whether q is negative or positive doesn't matter because you have q squared here. So even if you have negative charge, you make it point charge, the contribution of that single point charge, the self-energy of that point charge is positive infinity. Sounds good?
Wait, so the
I
second
We
equation.
just saw there are 5 text messages. Laugh my ass out. Okay, thank you. I don't know what's 10:03. Okay. Any question? Okay, so it's 10:44. Two other points I want to discuss, but you know what? I rather not to discuss because those are conceptual and important points. I rather stop teaching now, and on Tuesday I'm gonna recap this part only very quickly, and I'm gonna discuss two more points about the energy, and then we're gonna move on to conductors and then capacitors. Sounds good? So I had a quick discussion at the beginning of the class. Later today, I'm gonna send you an email with a list of the homework for chapter 2. I'm doing that today so that I can give you 2 weeks to finish the homeworks. And hopefully that gives you more time, and then you will have time to do more in-depth analysis of the problems and work more on those. And then homework number 1, you will get the answers, results back, and grades back from the grader of the course pretty soon. I talked to her this morning, so probably today or tomorrow you're gonna get the grades back on those. Okay? Any question?
Nope.
Nope.
Okay.
I'm gonna stop now, and you guys have enjoy the rest of the day. You will receive emails from me later today. Okay?